Good morning, folk. My name is Murray Jones, and today I'm going to use this thing I found in my backyard to teach you about transfer functions. Now, a transfer function is basically just a relation between the input signal to a circuit and the output signal. So we saw something very similar yesterday where we talked about amplification factors for MOSFETs. That is really just a simple case of transfer functions. So when we have a circuit that's going to amplify a signal in such a way that the amplitude of the output is just a multiple of the amplitude of the input, then that's okay. The amplification factor is just one number, and that's what we saw with the small signals I was shaking around a rope yesterday. Amplifying those with a MOSFET, it's just a ratio of the amplitude. But as soon as you get some more complex components like capacitors and inductors involved, that's where it gets a bit tricky, because those components have a time and a frequency dependence. So their response is going to depend on time and therefore on the frequency of your input signal. So what we're really trying to do today is put some maths to this. Give a mathematical function that can translate the input of a circuit to the output of a circuit without having to consider all the gutsy bits in between if we can help it. We'll have to consider them to find out what the transfer function is, but once we know it, that should be all we need to know. That's the ideal scenario. But before we get into that, we need to understand a bit of how the mathematics of an oscillation works. So yesterday I shook up and down a rope and we saw that small signal, but we need to understand how to put some maths to that, and that's what I've got this for. So when I shook up and down that rope, we saw a sine wave, right? Now, I want you to consider a different take on a sine wave. I've put this orange dot on this, I think it's the top of a table here. I'm just going to walk over here and roll it along the ground. Right? Now, if future me is as good at video editing as I think I am, then you'll hopefully have seen a bit of a sinusoidal trace going along there from the path of this dot above the center. Like, it's literally just the altitude difference at a point in time. And that is what we're going to be mathematically modeling. LEB. Using the premise of a circle. So we can change the height of this, and that's like changing the amplitude. And we can change the starting angle, and that's like changing the phase. So instead of considering the whole sine wave, we can consider it as the phase and amplitude of something that we assume to be circular. Right, now let's just take a moment to compare these two waves. One generated by me waving a bit of rope up and down in my living room, and the other by me rolling a decapitated table across my yard. Both of these waves have a wavelength, OVA so far, and both of them have an amplitude, which is half of the distance between their peaks. From a mathematical point of view, we can express both of these waves as something like this, where we have the wave as a function of time is equal to its amplitude times the sine of an angular frequency, omega. That's the frequency, the number of cycles per second, multiplied by 2 pi. Now, it's interesting why we multiply it by 2 pi, because we've got 2 pi radians around this circle here. That's 2 pi is a number, it's about 6 and a bit. And 2 pi radians means we've got 6 and a bit radii of the circle to get right the way around the circumference. So the angular frequency is essentially just frequency, cycles per second, but we convert the units to radians per second because, well, you'll see why in a minute, but radians come in really handy today. They're going to come in extremely useful. Now, the last term we got here, apart from the time, which is multiplied by the frequency to actually get something cyclic, is the theta, the initial angle. So this is the initial angle, the phase of our wave, the initial angle of our wheel. Right? Now, this mathematical basis for a wave, look, it holds for a rope being waggled up and down in a living room, and it holds for a sine wave generated from a decapitated table rolling across my yard. But what it also holds for is an alternating current. The small signals that we've seen in our MOSFETs and the oscillating currents that we deal with a lot in electrical engineering. Right, so you might be wondering, why do we need to get so fancy about it? Like, we've got resistors that essentially just scale voltage to current. The two are proportional to each other. It's just straight out of Ohm's law all the way across. And we've seen MOSFETs, which are basically like voltage-controlled resistors, but there are a couple of components that can be a bit more complex. For example, the capacitor. Because in a capacitor, we've got two plates and we have a charge across the plates. And the voltage will be proportional to that charge across the plates. However, the current is proportional to how quickly the charges are accumulating onto the plates. So the current and the voltage will actually be out of phase. The voltage will lag behind the current by a phase shift of 90 degrees. That means when our voltage is greatest, when we have all these charges on the plates, the current is zero, because this is the turnaround point between the maximum number of charges on the plates and the charges beginning to leave the plates. And vice versa, when the current is maximum, we have a whole lot of charges leaving the plates and arriving on the other plates, and the net voltage between them is going to be zero. So we have this phase delay, and this is what we need some interesting math to deal with. Inductors are a similar case, a bit less common, but they do it the other way. Inductors delay current behind voltage. So when the voltage is maximum, the current will be zero in an inductor, because the energy is being stored in the build-up of a magnetic field. The exact details of how that work aren't too important, but just remember they essentially do the opposite to capacitors. They delay current instead of voltage. And this is essentially a schematic of that. I had my orange dot on the wheel, that could be right about here for the voltage, and then if I were to try and put the current on the same wheel, that would be a separate dot 90 degrees offset to make the second wave. And in that way, the sine waves can be generated using this circular structure. Right, so now to actually be able to put some numbers to this, we're going to have a bit of a closer look at the mathematics of this current voltage relation. Now, we could just take some derivatives, but yeah, that gets a bit complex quite quickly. So there's actually a better way to do it, and that's what I'm going to explain right now. First, let's just consider this oscillation for a capacitor. We have the voltage lagging the current like so, and if we want to consider the points where the voltage is going to flip from a maximum or a minimum, that'll be 180 degrees out of phase. So that's like something pointing up on my wheel, like the dot directly above the center to the dot directly below the center. Now, I could just call that 180 degree rotation, or I could call it multiplying by -1, right? Because I go from, one amplitude above the center to one amplitude, -1, below the center, and that is essentially equivalent to just rotating all the way around. All I'm doing is just flipping it straight up to straight down instead of doing the whole rotation. So you'll agree that mathematically, 180 degree pi rotation is equivalent to multiplying by -1 in this case. Now here's where it's going to get really clever. Because what I've done here is I've just taken this signal and squared it, right? It's the same signal, but all I did is square the whole thing. So this blue line is the square of this blue line, and because it's a square, it doesn't have negatives. But it's still an oscillating signal. And if we wanted to consider the amplitude of this signal, what we'd need to do is adjust it, shift it, to be around a center line. So let's just do that, right? So now this is the squared signal, but all I've done is shifted both of the signals to be around the 0 line. Right, so that's not so tricky, but now there's a very interesting thing that happens. We can see that if we want to flip from the up to the down here, we only need to move half as far. So this is half of the distance. It's pi on 2 instead of a full pi rotation that flips our squared signal from the up to the down. But the pi on 2 still corresponds to a -1 flip, right? It's going all the way up here to all the way down here. That's a -1 multiplication to flip that. But the actual distance, the actual angle it's gone through here on the squared signal is only pi on 2. Right? So now here's where we can get really quite clever, because on our original signal we had the option of flipping from top to bottom by multiplying by -1. But what if I just wanted to shift by a smaller amount, pi on 2, instead of a full pi 180-degree rotation? So now here's where we're going to do a very clever thing. If in the squared signal a pi on 2 rotation corresponds to a flip of -1, what is a pi on 2 rotation going to correspond to in the signal that's the square root of this? It's going to correspond to square root of -1. Now that is quite clever. The square root of -1 multiplying onto our signal rotates by pi on 2. Now just take a moment to admire the mathematical beauty of this. Because, you know, if we were going from here to here we could multiply by 0 and bang, that's okay. But if we're going from here to here, that wouldn't work. But multiplying by root -1 will do this rotation for us. Now, there is a small catch to it, and that's that we actually need to be in different coordinate systems between the start and end point of this rotation, but that's okay, because our rotation is between voltage and current, which already have different units. So in our capacitor, if we want to say that the voltage lags the current by 90 degrees by pi on 2, then we just throw in a j, which is the symbol for the square root of -1, because square root of -1 is a bit of a mouthful to say. So we throw in this j, and that right there is our lag of pi on 2. And then this omega c is just the ratios of, you know, the capacitor. You can calculate it out of the area of the plates and the charges and whatnot. But this j is doing the grunt work. That's giving us our lag between these signals. It's giving us our 90-degree rotation between the 2 points on the circle. Now we can rejig this a bit. This formula of I equals something V is a bit unusual. We're used to V equals IR for resistors, so let's make it look a bit more like that by rearranging the equation. V is I on j omega c, right? So this j omega c gets called the impedance. Because it's kind of like a resistance, but it isn't a resistor, so we can't call it a resistance. So we call it the impedance. And you'll notice that, well, in this equation, actually, it's a bit easier to see here. If we have extremely high frequency, then the current is going to be proportional to the voltage, right? So this tells us a very important thing about capacitors, that we do have this lag, and also that high frequencies are going to go straight through them. And as a matter of fact, that is usually enough information to solve most passive filtering questions. Because if you see a capacitor going to the ground, the high frequencies are going to go straight through it to the ground, get sucked out, then you've got a low pass filter. If you've got a capacitor between your input and your output, then the high frequencies are going to go straight through it and you've got a high pass filter. So this one rule, that high frequencies go straight through capacitors, is basically the key to solving any question on filters. And this is the equation that it comes from, and the reason we can get this equation is due to our very nice trick with using the square root of -1 to do a 90-degree pi on 2 rotation and make this voltage lag behind this current. Right? Now we can of course do a very similar thing for inductors. Inductors, it turns out to be the reciprocal, so V is j omega Li, and the impedance is just this bit right here. right? And as I said, inductors basically do the opposite of capacitors. Capacitors store energy in an electric field, inductors store it in a magnetic field, and from electromagnetism, those two things are very intrinsically related. So this is doing a very similar thing. All it's doing is rotating by 90 degrees the other way, right? And that's why we have our J term in the numerator here instead of in the denominator, as we had for the capacitor. Right. Now another point I should just mention here is something that you're almost certainly going to see somewhere. That's called the Laplace domain. And Mr. Laplace, I'm sure he was a very nice guy, and he got this named after him. He said, well, J omega shows up in this equations a lot. That's the square root of -1 times the angular frequency. That shows up a whole bunch. Let's give it its own symbol and we'll call it S. And he managed to get that named after him. How can I get something named after me? Anyway, that aside, let's jump in and put all of this together. Let's actually calculate a transfer function. Now, the key to calculating transfer functions is impedances. So we've got all of these things like capacitance, inductance, resistance, and on their own they're a bit of a mix and match. You've sometimes got to put them together with reciprocals, sometimes not. But with impedance, it's all the same. You just put them all together the same way as you would if you were dealing with a resistor, right? So our formula for the transfer function is the output signal divided by the input signal. And our output signal is going to be over here. Here's our output relative to the ground, which is right here. So from the point of view of this output signal, we're going to have this and this in parallel with this resistor, right? That's the pathway to get from here to the ground. And these three components in parallel will be the impedances that contribute to it. For our input signal in the denominator, it's a similar thing. The pathway from here to here is this resistor in parallel with these three, right? So that's R1 plus this lot in parallel. Now we just combine them in the same way as we do resistors. 1 over the sum of the reciprocals. That's how we always combine impedances. And we get this big ugly thing here, which is actually the transfer function. Like this is, if they said find the transfer function of this is the valid answer to the question. Okay, there's your transfer function. And that's going to relate the output signal and the input signal, which is a really useful thing to be able to do because we want to know what the signal's going to be like at this point in our circuit when we're given a particular input, right? Now, there are a few very useful things we can do with that, and this is the most obvious. This is the filtering. So like I said, you don't even need to calculate the transfer functions. You can just look at these and remember that high frequencies go straight through capacitors. So here I've got a capacitor between our input and our output. High frequencies are going to go straight through it. Whoop, this is a high pass filter because the high frequencies go past. On this one, high frequencies are going to go straight through the capacitor. Whoop, they end up in ground. They don't end up at our output. So it's only the other frequencies, the low frequencies, that are going to end up at our output. So this is a low pass filter, right? So those are fairly obvious in and of themselves. But if we so desire, we can still calculate the transfer functions for them. So in this case, the transfer function, it's going to be the output impedance divided by the input impedance. So the output impedance is from here to ground, it's just this resistor. Input impedance is going to be from the input to ground, which has the capacitor and the resistor in series. Right? For the low pass filter, we've got essentially the same thing. The input impedance on the denominator is just this resistor and capacitor in series. The output impedance is from the output to the ground, which is just the impedance of this capacitor, which is 1 over j omega c, as we saw earlier. That comes out of the V equals 1 over j omega c I thing that we saw, which is an analogue of Ohm's law for impedance. We saw that on the slide with the capacitor. And the thing is, these are called passive filters because they don't have op amps in them, right? Or MOSFETs or anything else complex. Passive filters, which just have resistors, capacitors, and inductors, are only ever going to have a magnitude of the transfer function less than or equal to 1. And we'll get to what that means in a moment. Active filters are where you do have op-amps in the system. There are essentially two basic arrangements for them. This is the inverting arrangement, you can tell because it has the minus sign here. This is the non-inverting arrangement where the input is fed to the non-inverting input, the sign with the plus on it, and that has this form here. These are general impedances, we denote them Z. There'll be a whole bunch of components there, maybe a resistor and an inductor in series, and you'll just have to find out the total impedance of both of them by combining them, plug that in, and most active filters questions will fall into one of these two categories. There are a few other curveballs they can throw, like the Sallen-Key topology, but if you see it, Google it. Hopefully we don't need to use it too often. Right, decibels are another thing that Rata mentioned quite a lot, because the magnitude of a transfer function is typically written in decibels. What is a decibel? Well, it's 1/10 of a bell. But more importantly, it's a logarithmic scale where power is halved when you have -3 decibels. So if you have a signal that's 20 decibels and you reduce it to 17 decibels, your output power is going to be halved. We can calculate the magnitude in decibels just by taking 20 times the 10th logarithm of the modulus of the transfer function, and that's it in decibels. Modulus of the transfer function you can just find by taking the transfer function, multiplying by a complex conjugate, and taking a square root. It's the same way you'd find the magnitude of any complex number. I'm hoping you've seen that one in a math course. Phase. We often write phase with this symbol here. Phase is just our starting angle. Remember, this is a symbol for an angle. You'll see that once or twice. It's just important to know what it means. Octaves, we really hope we don't have to deal with octaves. They're disgusting. But if you need to, it's a fairly simple conversion. From 20 decibels per decade is 6 decibels per octave. And yeah, that's... both decades and octaves are fairly ugly systems to have to deal with. Just I hope you don't have to deal with them more than writing the name, which quite often you don't. Right, Mr. Bode. Look, I got to put this out there. I do not like Mr. Bode. Mr. Bode is the king of very big approximations. I would not even be mentioning Mr. Bode except that he gets a decent chunk of the Elect 2104 course and is probably worth quite a few marks. What Mr. Bode did was say, look, we've got this frequency response, we've got this transfer function, it's a curvy line, but I, Mr. Bode, do not like curvy lines. Let's just assume it's straight. That's his life's work there. He's gone and said, this curvy line is actually straight. It's a good enough approximation for me. Which it's a terrible approximation as far as they go. We saw some approximations the other day for the channel length modulation on MOSFETs. Those were very good approximations. This is not a good approximation. This is an approximation that will leave you with fried electronics if you actually use it in a real life scenario. But it still gets taught in this course, so let's take a look at it. We've got a logarithmic scale of angular frequency, and we've got a logarithmic scale of our magnitude in decibels. And what we do from there is we essentially take our big transfer function, that was the big whole thing I showed before, and we do some algebra to get it into this format, right? So we've got A ref is just the constant out the front, amplitude reference it stands for, or analog reference, whichever you prefer. We do some algebra to get that into this form here, where everything is in the term of 1 plus s is j omega, divided by a frequency, an angular frequency. So omega z is for a zero, as Mr. Bode called it, and omega p is for a pole. So when we have a zero, the magnitude is going to be 0 for omega's less than the 0. That's just the contribution of this term right here, one of the zeros, and it's going to be increasing at a slope of 20 decibels per decade for omega is greater than Z1. And the phase follows these relations as well. It's 0 decibels for omegas less than 0.1 times the position of the 0. It's linear between 0.1 and 10, and it's exactly pi on 2 for omegas greater than 10 times the position of the 0. Look, these are the straight lines that Mr. Bode has drawn for us right here, and for some reason we have to use them. Poles follow these relations. They essentially slope the other way. Those are the ones in the denominator. If we plug all these together, then we essentially use these cases for this term, this term, this term, this term, each of the terms that we see. We add them all up, and we add them to our analog reference term, which is what we'll have when we actually hit the 0 frequency. And from that we get a Bode plot, which is, a bunch of lines at different gradients in different points, and it's an approximation for the actual curve we get. To calculate the actual curve, we'd probably need to solve it numerically with Python or MATLAB or something, which actually isn't that hard to do. It's quite easy to do. I don't know why they're not teaching us that in this course, but they're not, so we'll have to do without it. Yeah, that is transfer functions. That is transfer functions in a nutshell. So we had a look at the phasor domain. That's all about pi on 2 rotations with the square root of -1 doing the rotating for us. We had a look at the transfer functions. That's the ratio between the output impedance and the input impedance. And we had a look at Bode's format for doing that, which is just a whole bunch of algebra and the fattest approximation on the planet. Right. Thank you for listening to this hopefully intuitive guide to phasor domains and transfer functions. Let me know if you'd like to see more similar videos, more similar topics. Let me know what topics you'd like to see. I don't have any other particular plans in the work. If there's another topic you'd like to see, look, tell me, maybe we can do another one. And yeah, I hope you found this helpful. Have a very nice day.